Welcome to ExplainerCast Episode 4. I'm your host, Dave Smith.
And this is Shane Swenson.
And we have some explaining to do. Today's topic is Moore's Law.
Yeah, so there's a lot to be said about this. It's essentially defining how our world works today with the explosion of the internet and computers and cell phones and streaming video on our cell phones, and now with generative AI and all of the large language models, it really has defined our technology capability in the modern era. And so we thought it would be good to start at kind of the beginning of this process with the development of computers and talk about how we got to where we are today.
Yes.
One of the key things about that we need to get into is this thing called Moore's Law.
It is very timely because I just discovered that the person who coined Moore's Law actually passed away only 3 months ago.
Oh, I hadn't heard that.
March of this year, Gordon Moore passed away, for whom this law is named.
Okay, so let's talk a little bit about who he was. So Dave, what was he up to in the 1960s?
Okay, so Gordon Moore was, I don't know too much about him. I think Moore's Law, this is one of those situations where his law, so-called law, we'll put law in scare quotes,
Yeah,
because it's not really a law. Like so many things that people say and then turn into interesting quotable things, they're not actually a law. It's not a law of physics. But anyway, Gordon Moore was the co-founder of an early semiconductor company called Fairchild Semiconductor, and then later Intel. And Intel is something that, I think fewer and fewer people nowadays will know what that is, because we don't see the Intel stickers on all of our computers anymore.
yeah.
But it used to be almost every computer you could buy in the 90s and early 2000s had a little sticker on it that said Intel inside. And that's because this company was named Intel they were the biggest manufacturer of CPUs, which is the core thing that does all the math and thinking and brain power of your computer. They created, essentially, I don't want to say they invented it, but Intel basically was the first mass marketer of CPUs.
Yep. And so essentially, and he became the chairman and president of Intel. And so he was in this early era of the semiconductor industry. And I guess I don't know how far we want to get into this, but semiconductors are really interesting materials. We can talk about with electronics, conductors like copper, zinc, iron, the things that you would make wires out of. They conduct electricity. And then you have insulators, things like plastic, air, that prevent the flow of electricity. And so you can wrap a conductor in an insulator, and that's how you make like a cable that's safe to handle. And semiconductors are an interesting material that, depending on the circumstance, and specifically depending on the electric and magnetic fields around them or through them, they will either conduct electricity or not. And so they allowed the building of materials and devices that essentially had built-in electronic switches.
Yes.
By hooking those switches together so that some of them controlled others, you started to be able to create these devices that could perform computational tasks, and they could compare values and give you maybe the addition of two values or the subtraction, or tell you which one was larger. And then based on that, people developed programmable devices that became programmable computers, where essentially you give them a sequence of instructions and the data you want to process with those instructions, and they could perform that computation. And that's what's become the modern computers we deal with today.
And it's really cool that these things really are just a giant mesh of little switches that when you turn them on and off in just the right configuration, they can actually do instructions you give them. And instead of having a physical switch that turns them on and off, you can actually use electricity to control the flow of the electricity.
Yep.
So they call this solid state. There's no moving parts inside these things. It's just electrical signals that tell other electrical signals whether to go or whether to stop.
Yep.
And that is right at the heart of every computer.
That's right. And that's important. Before that, people made devices like this with mechanical switches. There's a device called a relay.
Right.
That's like an electronically controlled switch. But of course, those were big. Like they would fill a room. They used a lot of energy. They were slow.
They were hot and loud too. They would actually click every time one of them switched.
Yeah, so a nuisance to be around. And so with semiconductors...
Actually, honestly, I wish my computer would click when it was thinking real hard.
Give you a little bit more insight to what's going on.
Yeah, clickety-clickety-click.
There you go. And so with semiconductors, then this enabled these these more tightly packed and really compact devices that had no physically moving parts. They were just moving really electrons and charged particles around. And so we call them solid state because they're just kind of one hunk of solid material
No
and
moving parts.
no moving parts. And they also got the term integrated circuit, which refers to the fact that instead of needing a separate set of components and wires to connect them together to make an electronic circuit, it was all just built into the chip, into this single component and integrated. So hence integrated circuit. And once that technology became available and people started essentially building computation and computers on those integrated circuits, or even simpler devices, this is really what led to what we see as the computing revolution. And Gordon Moore and his compatriots at Fairchild Semiconductor and at Intel and at other companies like Texas Instruments all got into the manufacturing side of this and really led to the development all the way out to present day. And so,
Yep.
So should we talk about now what, with that as the backdrop, what exactly was Moore's law?
Yeah, so I'll take a stab at this one. So Gordon Moore, I believe that this was based on observation. I don't think it was a theoretical proposition. I think he was watching what happened to the products that they were manufacturing and came to the conclusion that there was a rate at which the amount of componentry you could cram into this tiny little thing, which, by the way, just a quick side note, these things are not big. Like we talked about relays filling a whole room. These are like the size of what, Shane? Like a postage stamp?
Yeah, or smaller. I think of them as like my pinky fingernail.
Your pinky fingernail, like a single layer of material that's the size of your pinky fingernail. So Gordon Moore observed that every year, originally, the number of components you could put into that size, into that fingernail-sized integrated circuit, would double about every year. And here, by component, they mean like the transistors, which are the little switches that we were talking about. And I guess there probably were other components too, but primarily transistors, right?
Yeah. Transistors or like little pieces of memory would be another example.
Yeah, which are themselves composed of transistors, I believe.
Yeah.
Maybe?
Yeah, they would be.
Okay. Anyway, so not to get too pedantic.
Fair enough.
That is kind of the fun of this show. So every year he observed that these would double. And so he, I don't even know if he came out and said, this will forever be the case, that the number of components we can cram into this circuit every year will double. I don't think he probably ever declared it that way, but people just observed that he said it. And then more and more, it kept holding true. Year after year after year, these companies were able to double the amount of stuff they could put into these circuits. And that has pretty much held for 50 years.
Yeah, which is remarkable. And I think in his original observation, and he wrote an article that was published, I think in around 1965, where he put this forth. And I think at that time he said, I don't know how long this will go, but it looks like at least over the next 10 years that this will continue. And that's a pretty long time to make that level of a prediction for.
Yeah.
But I don't think most people would have expected it to continue to present day. And yeah, we're talking about in 2 years we'll be at the 60th anniversary of that article.
Oh my goodness.
And so it's not still doubling every year, and we'll talk about that, but the predicted end of this pattern of what we call exponential growth has been in the news for a long time. And so far, every significant impediment to continuing this doubling, maybe not every year, but maybe every 2 years, that there have been ways to overcome all of them so far. That we still shouldn't expect it to go on forever. It'll probably be some paradigm shift, like say quantum computing, that eventually kind of picks up the mantle. But for now, it's still going.
And at that point, when we have a paradigm shift, we'll just find a way to redefine Moore's law a little bit so that it continues, I'm sure. Because we've kind of cheated a little bit in that same way. And I might be wrong about this, Shane, a little, but I think... as I say it out loud, maybe I'm wrong. We'll see as we get toward the end of this episode if we can really say that that Moore's law in the terms that he defined in 1965 has continued.
Yeah, and I think it's already. I mean, he had a very specific definition, which was based on this device count on an integrated circuit. But the reality is, we've taken Moore's law and it's become something else in practical terms, which is that the capability that we expect in a computing device, which again, at the time that he defined this, I mean, a computer was something that sat in a large room and filled one or more large
Yeah.
cabinets. And now, we have very small computers, in wearable and mobile devices and embedded devices. And so what we really have come to take from this is that computers are smaller, they're faster, as in they can perform more computations in a time period. They're cheaper, they use less power, and as a result, they become ubiquitous to us. And so that to me is the practical outcome of Moore's law. And we can talk about the techniques that get us there. And so I think when you look to the next generation, it won't necessarily be more devices on the same or more components on the same device, but it might be more computational power available at a given price, size,
Right.
and power.
Yeah, exactly. So let's talk a little bit about the fabrication and how that plays into Moore's law of these things.
Okay.
I think it's fascinating to think about the history of what must have taken place here, where prior to the semiconductor fabrication industry existing, fabrication in general was all about taking big parts and putting them together and making machines out of them.
Yep.
Everything from cars to record players, so small and large things. But this semiconductor fabrication was about putting parts together that are so small you actually can't even see them with the human eye.
Yep.
And this was true even in the 60s and 70s when Intel was just starting out. And we were looking at this here, but the way that this is described, or rather the categories of evolutionary improvement on the fabrication process for semiconductors is described by the size, the minimum size of a component that these fabricating processes can produce.
Yep.
And they used to be described in microns, which is 1/1,000,000th of a meter, right, Shane?
Yep.
Or,
yep. So
is it
1,000.
micron or micrometer or both?
Yeah, a micron. And so that's also, or a micrometer. And so that's 1,000th of a millimeter or a millionth of a meter.
A million. Oh, yeah. So anyway, very, very small. In fact, about 1/5 the diameter of a human hair. And that was the biggest ones they ever made.
And that was the 10,
in
the 10
in
micron
the
size was the...
Yes, exactly. The 10 micron size was the first fab size. And then there have been, a couple dozen generations. And now CPUs are being manufactured at 5 nanometer size, meaning that the individual wires and components and traces inside these circuits are only 5 nanometers, which is 2,000 times smaller than the 10 micron components that were made in the 70s, which is just mind-blowing to me.
Yeah, it's crazy. And so when we talk about how they do this, it might be worth mentioning the technique because, we don't have machines that can like carve these out or kind of hand, you
Right.
can't build these by hand. And so
You can't 3D print them.
no. Though the technique used is an interesting one, and it's something called photolithography. And the idea then is you're using light. So photo means light, and I think lith means like stone or etch. And so photolithography means you're etching with light. And so the way this works, I think it's worth describing briefly. So the material that's used for this is silicon, which is an element that occurs widely in nature. It's essentially what sand and glass are made out of. And so in these cases, the manufacturing process takes very pure crystalline silicon and slices it into what are called wafers, and then essentially uses a certain type of light shining through essentially a mask pattern that marks where you want to leave material and where you want to etch the material away. And when you shine a light through, you essentially make like a photo image, and then they'll use like an acid to etch away. And I can't remember right now if it's all the places that were exposed to light or all the places that were protected from that light will be etched away, leaving behind now the surface construct that you specified with the mask. And so that process size, that 10 microns in 1971 down to say 5 nanometers or smaller today, tells you how small can the features in that mask, or how small can that grid on that mask be. And so it's taken essentially a series of improvements in the precision of making those masks, and making those masks at high enough reliability that the parts will come out representing the structure that you asked for, in order to make ever smaller scale parts.
Oh, it's amazing. It's just incredible. I honestly can't even believe it works.
It is sort of ridiculous when you think about it. And of course,
Yes.
and I guess the next thing that we'll get into is, we've talked about this being an exponential process. So when you repeat this, say, doubling, every couple of years or every year, then essentially that has this multiplicative, it's a multiple of multiples over time. So if you double in the first year, you've got twice as much. If you double again the next year, you're at 4 times as much. You double the next year, you're at 8 times. And so you're growing very quickly, and we call that exponential growth. And typically, when you see an exponential process like that, there's some element of reuse of a previous generation's capability to make the next generation. And then you use that new generation's capability to make the generation after. And so, like, bacteria in a petri dish will do this until they run out of food or room. And in this case, it's because we can make better computers, and then we use those computers to make better tools to make even better computers. And so that's the feedback loop taking place here.
Oh, yeah. Of course, that makes sense. If we were starting from scratch today without computers, there would just be no way to actually design these manufacturing machines.
That's right.
To do this.
Yeah, you have to start earlier in the process. And even another thing to think about is, so there's the precision of the machine, but there's also the complexity of the components, because you're able to literally fit twice as many components onto the same integrated circuit. You made the problem of chip design and chip layout at least twice as hard, maybe more if those components interact with each other. And so you're not laying those out by hand and on a big, computer-aided design sketch tool. You're using a computer to build the design based on your specification. And again, that computer is running on the previous generation of chips. So even the tooling on the design and layout side is recursive here.
Yeah. Oh, fascinating. That's right. Because it really does, just laying out a chip with that many components on it really exceeds the human brain's capability of doing.
Absolutely.
That. Like, we just couldn't do it without computer assistance. Okay, so Shane, we talk about doubling every year, and that was true for some time. Most people, I think, agree that we're not exactly doubling every year. I remember hearing in the 90s and early 2000s, it's actually more like 18 months now.
Yep.
And now I'm hearing people say every 2 years. What does this mean?
Yeah, I think in the early days of the technology, there was so much opportunity for easy improvement that, again, scientists and engineers figured out how to make that improvement, double every year. And that probably held up for that kind of decade that Gordon Moore predicted. And then essentially it's just been that the improvements have been more difficult to come by. They've been more technically challenging in many ways. And so the result is it takes a little longer than that 1 year to get to that full doubling improvement. It's taken, like I agree with you. And in the 90s, it seemed like 18 months was the common answer up till about, I want to say 2005. And then things started to slow down because we were starting to hit some fundamental problems with the physics of how these devices work on the atomic scale, and actually running into quantum effects.
Oh my goodness.
And so that made it harder. And so a couple things, I guess, there. One is that they call each of these different reductions in the size of the component, or the size of the component scale, a process node. And if you look at the size reductions, they're not doubling every year or two. They maybe double every 4 years or so. But in doing so, because this is a little bit tricky to think about, because that, say we're cutting the size in both the width and the length of our components, maybe in half every 4 years, that results in actually 4 times as many components fitting in the same area. Think of a grid where you reduce the size of each dimension by a factor of 2. It's a factor of 4 total number of grid cells increasing over, say, 4 years, which is like doubling every 2 years.
Okay, yeah.
So that's
So
one.
you don't actually have to shrink your fabrication size by half to get double the number of components. In fact, you could shrink it by a quarter and maybe even get double.
Yeah, you shrink it. You reduce it by like 1 over the square root of 2 is how the math turns out, which is like
Okay.
30, probably about a 30% reduction. I would guess.
Yeah.
Could do the math, but I feel like this podcast is a little bit about not doing too much research and not doing too much fact checking
Yes.
and kind of doing
Right.
our best effort. Um, so anyway, I guess let's talk about a couple of the limits that have been hit though. One of those limits was that, again, we talked about these transistors where the simple way that they work is they have what's called a source, a drain, and a gate. And so you have a place where electrons can flow into the transistor, call that the source. You have a place where they flow out of the transistor, say the gate, the drain, and in between you have the gate, which can either block the flow or enable the flow. And then that's the fundamental component that's used to build all these computer chips. And
That's the light switch thing.
exactly. And the way it works is essentially you can open and close the gate using another electrical channel that then imposes a magnetic field that, or an electromagnetic field, I can't remember, that blocks the flow. And the challenge has been, if you get to small enough sized gates, and that's where this 5 nanometers is going to come in, the electrons, because they follow the rules of quantum physics, they don't have to stay where they are, and essentially they can probabilistically just jump across the gate. And they can show up on the other side, even though you told them they couldn't go across.
Yeah.
And so that's a problem.
Yeah.
And it took a while to figure out how to solve it. And the common technique was, it used to be that these devices were kind of two-dimensional, where you sort of think of like a wire for the source and the drain, and then the gate is kind of a wire that's laid across it, again, using these very fine devices. And one of the main things that was done was, well, let's make that, instead of just laying the gate wire kind of across, let's have it kind of surround or make a fin where it goes up, over, and around the wire that it's trying to block, so you get more field effect on it. So that helped. But again, it's unclear how much smaller these chips can get before the electrons just don't stay where they're supposed to at all.
This improvement you just described to try to stop the flow and the quantum effects, about what year was that?
Oh man, I want to say it was
Like round to the nearest decade.
in the last 10 years.
Okay.
Yeah.
So already in the last 10 years, we were already getting small enough that quantum effects were starting to break the accuracy of these chips. And yet we've continued to reduce the fab sizes consistently over that time frame. So when are we going to hit the limit of how small we can go?
Yeah, I think we've got to be getting pretty close. There's another limit that we are hitting, and I say we as if I have anything to do with this, but we as human society, I guess, we're all in it together.
Yes.
Okay. I have nothing to do with the engineering of these things, but I'm a fan of the engineering.
Yeah.
So another issue that's coming into play is that photolithography process, where you make a mask that's going to block the light in certain spaces, allow it through in others, and then etch away the material accordingly. That's dependent on the wavelength of the light that's used. And again, due to quantum and wave function physics, you really can't make features that are smaller than the wavelength of light. And so that's a fundamental limit, because that wavelength is measured in nanometers. There's a trick that's being used, I think, at this point, which is where you actually make 2 or more masks, each at, say, double the feature size you care about, and then you essentially do one mask, and then you use the other mask shifted half a wavelength or half a feature width to the side to do the second exposure, and you sort of cheat this wavelength concern, but there's probably limits to that. And so some combination of electrons and charged particles just not staying where they're supposed to, the feature size of the photolithography itself, and then another one is, as you get more of these devices in close quarters, and again, there are all these little switches, and the way computers work is they basically switch these switches back and forth depending on the commands and processing that they're performing. Every time you do that, you essentially are storing charged particles in one part of the chip and then essentially draining it away to kind of clear it and do your next computation. And so
Mm-hmm.
all the electricity you're putting into the chip to do this computation essentially comes out in as heat. And the result is that these chips generate a tremendous amount of internal heat, and it's becoming a challenge in physics to cool them enough so they don't melt themselves.
Right. Oh man.
I've heard that the amount of power being dissipated in the core of one of these chips, if they're fully activated at running at their full speed, that there's more power density there than like in the center of a nuclear reaction. Just very small and contained, but
Yeah.
but cooling them is a significant problem. And so there's
Just like a tiny sample of a nuclear bomb.
that's
Don't worry.
right, just a little one. I mean,
But
enough
it is
to,
in your pocket.
that's right. Well, and sometimes our phones get hot.
That's true. That's usually not. Well, I guess that is what's heating up in part.
Yeah, yeah.
Is
I mean, if
the
you notice
CPU.
this, I don't know if you still notice this, but when you're like watching videos or doing something that used to be really taxing on the phone, like it would get hotter, and that's
Yeah.
because it was using more of the computation capacity, and of course, it's draining your battery faster as well. But it was generating more heat that needed to be dissipated.
Yeah, you have to get rid of it.
Yep. In the phone, it just kind of comes out through the case. In your computer, you'll hear your fan start to turn on, perhaps, and try to cool that way. In large data centers, where this is happening at mega scale, when you're planning to build a data center, you got to think about not only the power that you bring in to power all the computers in that data center, but you actually have to think about how to cool that data center and essentially take the heat back out. And so when you see a data center, you'll see usually a bunch of power lines, but backup power generators in case they lose that power, but usually also a lot of some type of cooling system, some type of chillers.
Air conditioners usually.
Yep.
And they blow air throughout that place.
Exactly. And cool it maybe by evaporating water or something like that.
So I just want to go back to something you mentioned about light and the wavelength of light. We are now down to the point where our chips are manufactured with these 5 nanometer processes or smaller.
Yep.
And even in the 80s, we were in the hundreds of nanometer range. But here's what I don't quite understand. Isn't it the case that visible light, at least, has a wavelength in the hundreds of nanometers? What kind of light are they using to etch these things?
That is a really good question, and I am rapidly trying to find out. I'm going to need a minute on that one.
Ultraviolet light in the wavelength of 13 nanometers.
Yeah, so let's
Extreme
see.
ultraviolet.
Yeah, so the extreme ultraviolet is the relatively new thing. And it may not be that it's the full wavelength. It may be that the way it's used, that you get down to some fraction of the wavelength, but you can't go smaller than that. And I know like with the smaller wavelength, like the extreme ultraviolet, that was thought to be coming online for a while, but it was a lot slower. There were just, I don't know what all the challenges were, but there were just a lot more technical and engineering challenges than were anticipated. And so it took longer to bring online than the previous nodes.
That's very interesting. So invisible light, smaller wavelength, allows more precision, but probably a lot more challenge. It's probably a lot harder to generate high frequency. Oh, let's see here. Yeah, high frequency light at the power levels they need to actually do the lithography. I can imagine.
Yep. And I think there were issues again with like the reliability and the consistency and how to power them and so forth. And so kind of a set of engineering and physics challenges.
All right. Well, sorry for that little distraction. I just was really curious. There must be some crazy techniques that they're doing to make this work.
Yep.
So you want to go back to heat for a minute?
Sure.
It is kind of interesting how processors on your computer and in your phone and other devices, they are essentially, they take instructions as input and they produce heat as output.
Yeah.
I guess you could say.
And a tiny bit of information, but mostly heat.
Yeah. Heat is the important part. And you also mentioned they can get so hot they can actually melt themselves because they are, after all, made of the same material sand and glass are made of, and they don't really have a very high melting point.
That's right.
And so one of the challenges of Moore's law is actually that as these components become smaller, there is more opportunity for them to move more heat because there's more of them.
Yep.
But that means that you have to actually bring other physical elements in contact with them in order to dissipate that heat, which becomes more and more challenging.
Yep.
And so people have done all kinds of different things to try to solve that.
That's right. Yeah, I mean, initially it was just, well, you have, the chip goes in some kind of package with a case on it, and you make sure that there's reasonable thermal conductivity or heat conductivity between the chip and the outer side of the package, and so it would just dissipate heat that way. And then for higher power density, there are things called heat sinks, which would basically be like a piece of metal like a block of metal that has a lot of fins in it, and you put the flat side of that block of metal against the package of the chip, and then all those cooling fins allow the conduction of that heat away for more, into more surface area, so that the air could take more heat away. You can add fans that blow air across those cooling fins and do better. And then I've seen situations where there were systems that would either blow like a mist at the devices to cool them through evaporative cooling. And then I've seen immersive liquid cooling, where you just dunk the whole thing in a non-conductive liquid medium, because
now those are more for hobbyists, right? Like, have you ever seen that actually in kind of a production at scale environment?
No, but I feel like I saw an article in the last few weeks where someone was talking about like an underwater data center. Like, they were starting to think about, what if they just immersively cooled an entire data center?
The whole thing is submerged.
Yeah, basically. I mean,
it's pretty smart.
A whole separate set of logistical problems if you do that, but
yeah,
heat
scuba
won't be
diving
one of them.
to connect the Ethernet cable.
Yeah, that's right. But it'll stay cool.
Oh boy. Yeah.
But there's also what are maybe called closed circuit liquid cooling, where you still put that heat sink on, but just like kind of like the way your car cools the engine, is you then have liquid cooling channels in that heat sink, and you flow a liquid coolant through those channels, because of course the liquid has a much higher capacity to move heat out of the system than airflow does, being just a denser material. And I think I have heard that people are, at least certainly hobbyists, do this. I don't know if any commercial data centers are looking to do that type of liquid cooling as well. But
yeah, I don't know either.
The data center planning really is about power in and heat out, and so more efficient ways to do that are going to be welcome.
So, and heat dissipation is one reason, I don't know, maybe the only reason, that they don't stack these things up like a skyscraper. Because in essence, all of these CPUs are essentially single-story buildings.
Yep.
And you would think, oh, well, I can take Moore's law into the next generation by simply turning this flat sheet into a cube.
Yeah.
So then now I've got, again, like a huge increase in the number of components I can shove into that same space. But the problem is the ones in the middle have nowhere to put their heat.
That's right.
Except onto their neighbors, and then their neighbors will melt.
Yep. Yeah, because you're right. That would totally help you on the scaling side, because now instead of getting, we already have the X times the Y, the width times the length helping us, but you would have width times length times height. So you would actually have a multiplicative gain. But yeah, in the core of that chip, you would need some mechanism to extract heat from it, or it would just melt. And so I haven't seen any practical mechanisms to create high performance devices in the integrated circuit realm that are deeply 3D stacked.
For a long time, Moore's law was manifested as a clock speed increase. In the 90s we had the Pentium chip, and it was like 90 megahertz, and then they were like, the next year is 150 megahertz, and then 300 megahertz, and then we hit the gigahertz, and so I think a lot of people may have thought of Moore's law as the gigahertz law, which basically says that every 18 months the number of gigahertz that you can crank through a chip will double.
Yep.
But that's really not right. It may have tracked there for a little while, but a couple things. First of all, the clock speed of chips has basically stopped increasing.
Yep.
In, 15 years, maybe 10 years, something like that.
Yeah, I'd say so. I think, again, it was kind of between probably 2005 and 2010 that commercial chips kind of hit their peak, and they hit their peak around 3 gigahertz, which is 3 billion cycles per second. And then they kind of walked back down to kind of steady state at about 2 gigahertz. Mm-hmm. And I think what was happening was, again, for that era, especially in the 90s, when the personal computer came out in the early 80s and then became very popular in the 90s and almost ubiquitous in the 2000s. Um, the There was kind of this golden age of computation where the chips were getting smaller, and because they're getting smaller and they're moving fewer electrons around per operation, they were able to have those operations, occur more quickly, because you could essentially, the clock speed dictates how long it takes the computer to perform each increment of computation. So to go kind of from one set of the switching states to the next set of switching states and have all the switches flip that need to flip and arrive at their new position stably, that's going to be dictated by your clock speed. And because the switches were all getting smaller and they had less electricity to move around, they could go faster and faster. And and I think what started to happen though is, as you go faster, you're pushing more current, which is the flow of electricity, through these transistors. And the more current you flow through, they do become a little less efficient, and you lose some of that electricity as heat due to resistance in the chips. And so they started to run into the power density problem, which is, to clock them faster and faster, started to use more power than they could efficiently supply to the chip and efficiently pull the resulting heat back out. And so after kind of peaking at about 3 gigahertz, then engineers realized that they needed to scale back and go a little slower, but try to make up for it by doing more work in each cycle. And so the net result could still be a more performant device if, you say double the amount of operation it can perform in a given clock cycle, even if you don't increase that clock speed anymore.
Got it. And I don't want to put you too much on the spot here, but hey, it's not my first time. Why not?
Sure.
What is the more work? So I can think of a couple of examples. I can only think of one example, which is that one thing they tried to do is get a little more crafty about predicting the next state before they actually got the instruction to do it, which was called branch prediction.
Yep.
And so that was more of an efficiency gain, but that would have given them benefit regardless of whether they were running at today's clock speeds and today's fab sizes or 5 years ago. But is that an example where it's almost more like almost what I'd call a software optimization?
Yeah. So there were kind of two things, and one has ended up becoming the dominant solution. So the first way of trying to get more work was to define a more complex task for each clock cycle, and to say, could I perform a more complex computation, and or could I read farther into the future and process multiple instructions at the same time? So instead of, the way computers are programmed is, they have a very simple basic set of instructions, like load a number from memory, maybe add it or subtract it from another number, compare it to another number, and make a decision based on that comparison. And so one thought was, well, what if I define more complex instructions that do multiple things in one cycle? And that was something Intel was really focused on, especially in the late 90s, early 2000s, and they were doing pretty well at it. The problem was that to gain an increment of capability in that manner by making the instruction set more complex, like to get a factor of 2 improvement in the amount of work they could accomplish in one clock cycle, they almost had to double the amount of transistors on the chip to achieve that. And so it was a kind of a game you couldn't win in the long run. And what ended up supplanting that, and it really is the basis for the types of computation that are most ubiquitous today, and we'll go into how this is used in AI, especially maybe at the end of this episode, is instead of trying to do more complex tasking in a single instruction, let's try to accomplish more simple instructions on distinct problems we're solving at the same time. So what we would call parallelism. So maybe rather than trying to cram more into one operation, I say I can actually perform 5 separate operations on 5 separate tasks every clock cycle.
Right.
And then maybe I double that in a couple of years, and now I can do 10. And so any single linear or sequential program is not actually going to get faster in this paradigm. But if I can decompose the problem I'm trying to solve into multiple sequential instruction sequences, then I can run them all in parallel and I can still get more work done. And perhaps for certain applications, that's actually what I want to achieve anyway. And again, some of the modern like machine learning and AI applications fit that paradigm extremely well.
Yeah, that's very interesting. It's like we've been we've been able to make computers faster despite not being able to increase clock speed because of all these extra transistors, simply because we can just do more at the same time. And boy, has modern software taken advantage of that, which maybe we'll talk about that a little bit later, but
Yeah,
there is so much stuff competing for the CPU on my computer and on my phone all the time that it's a darn good thing that that CPU can do a lot at the same time.
exactly. And again, probably around the time you and I were both studying computer science, the focus was really on what we would call single-threaded programming, where you're kind of thinking about doing one thing at a time. And
Hmm.
in all high performance modern applications, heavily embrace what we would call parallelism, which is doing multiple things at the same time. And then going a step
Yep.
further, distribution or distributed systems where we actually have multiple separate computers working on the same problem at the same time.
Right.
And so it's use of parallelism both at the micro level on a chip, and then at the macro level across machines, in order to create modern applications. And that architectural shift, I mean, that really took place in the last 10 to 15 years.
Yeah. Yep. Exactly.
And so if we take that to where is Moore's law really driving change today? Again, in the 80s, 90s, first decade of the 2000s, maybe even, it was really these Intel, and there are a couple other manufacturers as well, but Intel was leading the charge on these central processing units, or the CPU, the main kind of decision-making brain in a computer. And your modern computer still has that, and it's more capable than it would have been in a computer you bought 5 years ago, but probably not a lot more capable,
Right.
in a lot of cases. But the part of the modern computer that still is gaining capability at a dramatic rate is what's called the graphics processing unit, or the GPU. And originally these were developed in the 90s, and one of the companies that did this was a company called NVIDIA. And they were really around rendering, especially three-dimensional graphical scenes for display on your screen in real time. And
Right.
this is one of those perfectly parallelizable problems because your screen is decomposed into a grid of individual what are called pixels, or light emitting elements, and you want to compute for every one of those pixels on the screen what brightness and color should it be, and then you just repeat this process very often. And so you can break your screen down into a grid and have a separate computation for what should show up on each pixel, or maybe on each sort of little patch of, a group of pixels. And you can run all those processes in parallel. And GPUs really were optimized around doing exactly that. And
Yep.
and so that's great. We got awesome graphics, and it was really cool for gaming and so forth. But then computer scientists figured out that some of the other interesting problems they were trying to solve, especially around AI training, and also the inference or the classification tasks that AI models would produce, those are also highly parallelizable. And people figured out how to use GPUs made by NVIDIA and others to much more efficiently perform those AI tasks. And that has now created this kind of new application synergy where the dominant market for GPUs are these high computation tasks. A couple of years ago, it was crypto mining is another one that was like that.
Yep. That's right.
You couldn't get a GPU for your gaming machine because the crypto miners were buying all of them.
Yep.
But all these AI models that we see out there, the ones that can generate images on the fly, the the big language models that you can now interact with in real time, those are all trained on, and they're running on GPUs, not to produce graphics, but to perform these other computations, highly parallel.
Yeah, which is one of the most amazing serendipities, I think, is the fact that, and I don't know if it's cause or effect, but the fact that doing graphic computation, which essentially boils down to tables and lists of numbers being multiplied and added together all at the same time.
Yep.
is essentially the same task that we need to do in order to produce these artificial intelligence applications. And it kind of makes me wonder, like, if we had developed some other technique for graphics, would AI have emerged from that technique instead? And would we have a very different, but very different implementation of the same exact kind
Yeah.
of solution? I don't know.
Yeah.
But it is just fascinating. And NVIDIA shareholders are very happy right now, just this week in particular, because they announced that they have sold more units than they ever have, and higher than expected sales by a margin that exceeds anything they've ever produced in the past, because of AI demands, because of all these different companies that want to buy this hardware from them.
Absolutely.
Which is just fascinating.
Yeah, definitely AI is having a moment right now, and NVIDIA is benefiting from it. And yeah, I actually wonder that too, how much the development pathways, because I studied some of these AI techniques in college, and at the time, like, you couldn't run a large neural network in any real-time fashion, and so it just wasn't that interesting to analyze like a 4-node network. And it was like, well, what can this thing ever do? Well, now
Right.
you put billions of nodes and you can run them on your GPU, and you can do these amazing tasks. And so I think the ideas were there, and their pathways have converged, and that convergence again has led to these applications that we're now seeing come to the fore.
It is amazing. And then, just to take that one step further, because these components are so small, now chip manufacturers like Apple, who has produced some pretty innovative chips recently,
Yep.
they are able to put multiple, like up to 8 CPUs and something like 10 or 12 GPUs and the system memory all on a single chip.
Yeah.
And this is just, it's just incredible that they can even do that and cool it and have it actually run at a reasonable speed. But that is the inevitable result of Moore's Law, I think. 50 years of Moore's Law means that all these components that used to be on totally different physical cards that were like, themselves the size of the envelope of a letter
Yep.
that you would send in the mail, are now actually integrated onto something that's the size of my pinky.
Exactly.
So, it's just proof positive that Moore's Law is still rocking, even though clock speeds have essentially stopped increasing.
That's right. And you make a good point there. The multi-core CPU, essentially saying, well, if I can't make one big CPU that can do more, I'll just put more of them onto one chip, and I'll expect that a modern computer is already trying to multitask. And so those multitasking, services can utilize all those cores. And so that's another way that Moore's Law has enabled more computation per cycle, for the same size, weight, and power budget. It really is quite remarkable.
Matt, I have great respect to you, Shane, for the number of times you use the word "more" to describe Moore's Law. It's just impressive.
I've got one pun in my bag today, I guess.
Okay, good work.
All right, Dave. Anything else we should talk about in this space?
Oh boy, I think my well is all tapped out.
Okay.
My knowledge has not doubled every year for 50 years on this topic.
So, yeah, I probably have one or two more things, and then I think we're probably done.
Okay.
One of these questions that keeps coming up is, which of these constraints is going to finally be the one we just can't overcome? Is it going to be the power, the leakage current going through these gates with quantum effects? Is it going to be the sheer power density just makes the chip so hot? And I guess other adaptations to that are that if you were to watch the power, or say the health meter on your computer, or if you had one on your phone, what you would see is you'd see a lot of the time that the chip is kind of idle. And so they now adaptively enable and disable different functions within it as needed. And they'll also change the clock rate in real time. So if you're not asking a lot of it, it'll run at a low clock rate, uses your less battery, runs cooler. And then if it really needs to do something high performance, it'll raise the clock rate, activate more of the chip. So this partial activation and dynamic clock rate has also helped, because we as human beings, we actually care a lot more about peak performance at the moment we want to see something, as opposed to average performance. Like we don't care what it's doing while we're sleeping. We want to see at this moment, I want to download this video and I want it to play in real time right now. And so that burstiness has also been another attribute that's been helpful. There are some out there, like really fundamental limitations. There's one that's based on, I forget which law of thermodynamics it is, that says that in a closed system, that you can't, the information cannot be created, and that you can only like go towards like more entropy in a closed
Yes.
system. And so there's
Yeah, the third law of
Is that
thermodynamics.
the third one?
Systems entropy approaches a constant value as the temperature approaches absolute zero.
Okay.
Is that what you're going with?
I should have looked this up ahead of time. Maybe.
Yeah.
I don't actually know. But what I do
just noticed there's a zeroth law of thermodynamics, which I never heard before. I don't even know what this means.
But what I
Anyway,
but what I
sorry, go on.
remember, let me see if I can recall this. Now, this is a few years back, but there's a thermodynamic argument about the fastest you can make a computation go on the basis of the reality that you destroy, or actually it's the power. There's a power limitation. So the other thing that's happened right now is we not only make things faster, but we can perform computations with less power per element of computation. And
Okay.
and so like if you look at a data center, they could build, they could probably put more square footage, or they could build them more stories tall. They often are actually limited by just the total power that they can bring into it and that they can afford to pay for. And so the economics
Right.
of computation actually come down to power. Your mobile device, it's really about the battery capacity, and the battery size and weight and life. And so I think of sometimes our modern world is, for computation, we're limited by the economics and distribution of power. And so Moore's law, is an indirect consequence of Moore's law, is that as we made things smaller and they use less power, then we get more computation for the same power budget. And a limitation that we eventually will hit on that is there's a fundamental unit of power required to destroy one bit of information.
Right.
And so today computers destroy most of the information. They destroy all the intermediate values. They just overwrite their previous memory with the new value as they're computing updates, through their instructions. And so you can look at that information destruction, and fundamentally that will specify like a floor for the minimum power that type of computation must consume. And so there are some weird ways around it. There's one thing called reversible computation, where you never forget any of the intermediate values, but you really replace now the problem of power with the problem of storage.
With storage.
Yeah. You also have to go really slow for that to work. But then the other is there are new paradigms like quantum computing, which just totally change the rules of the game and what it means to do computation. And so I think if at the beginning of the show you asked, well, how is Moore's law actually practically applied to our lives? And I think it's just that it's made computation cheaper, faster, more available. And even if we hit the end of semiconductor-based classic Moore's law scaling, maybe something like quantum or some other paradigm is going to take over and continue to deliver to our systems that growing capacity for computation on a fixed size, weight, power, and capital budget. So we'll see where it goes. But at the current rate, I feel like the last projection I saw, we were within probably 30 years of hitting that fundamental floor on power, if the continued trends were extrapolated out. So it's not forever.
So cool.
So with that, I think I'm
All
out.
right.
But it's been good to talk about this one with you, Dave.
Yeah, this is a fascinating one. I mean, the underlying theory and all the different things that are going on, just amazing. And just, I mean, my fundamental misunderstanding of clock speed being Moore's law, equal to Moore's law back in the 90s, the world is so much more complicated than that. It's just magic.
It certainly is. And it's remarkable what we have as humans have done in this particular domain and the effect it's had on so many aspects of our lives. And it'll be interesting to see where it goes from here.
All right. Thank you, Shane. This has been another episode of ExplainerCast. Thank you for joining us.
Thank you, Dave. See ya.